Hello everyone, welcome to this 15th lecture in the NPTEL course on Riemannian geometry. So last time in the previous two lectures we have introduced this notion of connections or covariant derivatives of vector fields, covariant or directional derivatives of vector fields, and then we proved a series of sort of locality principles which essentially shows that in various ways the connection is a local operator. The sort of best locality theorem or the most refined locality theorem was discussed in the previous lecture. So that essentially says the following: if I want to compute the derivative of y with respect to this vector xp, then this actually only depends on the values of y. So let me draw a picture here. So if you want to compute the derivative at this point p with respect to this vector xp, then all you need to do is take a curve which is tangential to the vector xp at that point and restrict and look at just the values of y on that curve. Okay, so this thing depends only on the values of y along this curve gamma of t. So using this one can write down a formula for computing the covariant derivative along points on a curve. So let's say I take this curve gamma, which is an integral curve of x, so that means x at gamma of t is given by gamma dot of t. Then you restrict your attention to the values of y on that curve gamma of t, you call that y of t. Then the derivative of y in the direction of x or with respect to x at a point on the curve at a point gamma of t is simply given by this formula. Okay. So here you see explicitly that all that matters is really the values of y on that curve gamma. It does not matter what values y has at even points arbitrarily close to the curve gamma. Okay, so using this we now want to in today's lecture address the question of defining covariant derivatives along curves. Okay, so that's going to be the subject of today's lecture. Okay, so I first need to introduce this notion of vector fields along curves. So this notion is actually going to be useful throughout the course. So let's do it a bit carefully. So vector fields along curves. Okay, so let gamma be a curve defined on some interval I. Let this be a smooth curve. Okay, so then a vector field along gamma is a smooth map x from the interval to the tangent bundle of M such that pi composed with x of t. So remember there is a natural projection map pi from the tangent bundle to M. So pi composed with x of t should be gamma of t, or equivalently all that it says is that x of t should be a tangent vector at gamma of t. Okay. So just to sort of draw a picture, you would have something like this. At the intersection point you would typically have two vectors because as you go along the curve at some point you again come back to that intersection point, right? Something like this, and then it continues. And so on, right? So this is a picture of a typical vector field along a curve. So the only thing you need to be careful of is when you come back to the suppose your curve intersects itself, then when you come back to the curve, to the intersection point, the vector field might now have different values, right? Because the vector field is a map on I, not on the image of the curve. Okay, so this is an important point to keep in mind. Okay, so we set x of gamma to be the set of vector fields along gamma. Okay. So what is the most sort of basic example? Of course, you can take the velocity vector. So if gamma is a smooth curve, the velocity vector is going to be a vector field along gamma, right? Just to give you one more example, one can take m is R2. So let's say I have this curve and I have these velocity vectors. So at each point I rotate the velocity vector. So this is something we already discussed, I think, in our second lecture. I rotate the velocity vector by 90 degrees in the counterclockwise direction, okay, and call that n of t. Okay, so n of t is basically this counterclockwise rotation of the velocity vector. So in coordinates, this is going to be minus gamma 2 dot of t comma gamma 1 dot of t. Okay, so that's another example of a vector field along a curve. Okay, so we say that x is extendable if there exists a vector field x tilde on some neighborhood u, where u is some neighborhood which contains the image of gamma, such that x tilde at gamma of t is simply x of t. So that means in this picture, if you have this vector field, you can draw a little neighborhood here so that you can and you have a vector field x tilde on this neighborhood which restricts to x of t on gamma of t. Okay. So note that such extensions may not always be possible. So note x may not always be extendable. For instance, as I alluded to before, if gamma has a self intersection, so there are some times t1, t2 for which gamma of t1 is equal to gamma of t2, and suppose x of t1 is not equal to x of t2, then obviously x is not extendable, right? So so this is also something to keep in mind. So the main proposition that I want to establish in this lecture is the following. So this is covariant derivative along curve. Okay, so let nabla be a connection on M, and let's say gamma is a curve, a smooth curve. Okay. Then nabla determines a unique operator, which is usually denoted by this script D. So this takes in a vector field along gamma and spits out another vector field along gamma, such that it has the following properties. So it's firstly R linear. So that means for all A1, A2 in R and for all x1, x2 vector fields along gamma, if you calculate this, then you get this relation. So that's R linearity. Then of course we also want a Leibniz rule to be satisfied. So for all smooth functions on the interval and for all vector fields along gamma, if you compute dt of f times x, that is just f prime of t times x of t plus f of t times the derivative applied to x, right. So this is the Leibniz rule, the analog of the Leibniz rule, and crucially, if x is extendable, okay, then for any extension x tilde, we have this. Okay. All right. So I hope the statement is clear. So let's prove this proposition. So we first prove uniqueness, and then the existence will follow from our proof of uniqueness. So we first prove uniqueness. So suppose dt is such an operator, and let t naught be a point in the interval. So then by the proof of locality, our locality results for the connection, it follows that this connection only depends the value of x on this small interval t naught minus delta to t naught plus delta for some small delta positive. Right. So, I mean, heuristically, you should think of this as the derivative of x with respect to the velocity vector. Okay. So the reason why this is well defined, and I'll write down the rigorous proof, but the reason why this is well defined is because we have already seen by this refined locality that the values of these covariant derivatives only depend on the behavior of x along this curve gamma, right. So if I'm calculating the derivatives with respect to gamma dot of t, then gamma is obviously an integral curve of gamma dot of t by definition, right. So then it's enough to actually just restrict attention to the values of x on gamma of t. So that's essentially why this operator dt is well defined, okay. So but anyway, let's write down all the details. So now choose delta small enough such that this entire segment of the curve is contained inside U, okay, where U is a coordinate neighborhood. So essentially you just take your gamma of t naught, choose a coordinate neighborhood around that with coordinates x1 to xn, then there is some small delta so that there is a segment of gamma around t naught which is completely contained inside this coordinate neighborhood, right. So then I can express my vector field x of t as some xi of t times some xj of t times del j, right, where t is now in this interval t naught minus delta to t naught plus delta. Okay, now note that this vector field del j is clearly extendable, right. So the restriction of del j to gamma t is clearly extendable because del j itself is an extension of this vector field. So then by the properties of dt, the properties that we demand of dt of x at any t naught, at this t naught is basically just given by the derivative of the kth component of x at t naught plus gamma ijk times xi at t times the velocity vector at t, this whole thing times dk. So I am going to call this formula star. So the point is that the properties of dt ensure that that this is uniquely determined. So this is clearly uniquely determined by this formula. Okay, so this proves that any such operator must be unique. All right. On the other hand, this sort of proves also the existence, because how do you complete the proof of the existence? Well, if gamma of t is, if gamma of the entire interval is contained in a coordinate chart, then you are already done, because one could just use this formula star as a definition of dt, right. Okay. On the other hand, in general, let me just draw a picture. So in general, you have this this curve gamma which might self intersect, it does not matter. So what you do is you cover this with open coordinate neighborhoods. Okay. So on each of these, our formula star gives you a definition. Okay, our sort of formula star gives you a definition of the connection, but the key point is that on the intersection, because of uniqueness, these two definitions must agree. So once they agree on the intersection, it's defined on all of gamma. Okay. So that's the way you extend this local definition into a global definition. Alright, now I want to use this covariant derivative along curves to define something called as parallel transport. Okay. So just to motivate you, let me give you a couple of examples. So the first example is, suppose you have a curve gamma in Rn, it works in all Rn, but let's just take R3 because we can draw maybe a picture here. Okay. Now, what do you really understand when you say that a vector field is parallel? So in Rn or R3 in this case, it just means that the vector field sort of points in the same direction all the time, right? So this is an example of a parallel vector field. In R3, right? So in other words, a vector field is parallel one sensible definition. If you also want to normalize so that the norm doesn't change, one sensible definition is that the derivative is 0. Okay. So that's a sensible definition of a parallel vector field in R3, right, or Rn. Now let's look at what happens in case you have a surface inside this Rn. So let's say for a concrete example, you can take the example of a sphere inside R3. Okay, so let me draw a picture. Okay, and suppose you have the following curve, and let's say you start with a vector here. Sorry. Let's say you start with a vector here. So now initially your vector, let's say V at the tangent space is actually tangential to M. Now suppose, I mean, M is sitting inside this Rn, so let's try to parallelly translate this vector as if it's a vector in Rn, right? But now you notice a problem, because as you keep sort of parallelly moving this vector, clearly at some point, or maybe almost instantaneously, this vector is no longer going to be in the tangent space to M, right? If you just parallel translate it as if it's a vector in Rn, it's clearly going to be a vector that's no longer in the tangent space to M. It's going to point sort of out of M, or at least it's going to have a component that's going to point out of M. Right, so if I want to still have a notion of parallel translation, so the following is a sensible thing to demand. So a parallel vector field keeps the direction as constant as possible while still lying in the tangent space to M. Okay. So it tries to keep its direction as constant as possible in Rn, but at the same time it also wants to be tangential to M. So the solution is that at each point you parallel translate as if you are in Rn and then keep projecting onto the tangent space to M. So an equivalent condition, if you think about it a little bit, is that the derivative will be perpendicular to the tangent space to M at gamma of t. Okay, because the only correction that's needed in order to make sure that it lies, it is still tangential to M, is a correction needed in the perpendicular direction. Okay, so the derivative is perpendicular to the tangent space at M, because that's the only correction needed to make sure that your parallel vector field comes back to the tangent space to M. Okay, but recall that on M we have a natural connection which can be defined by taking the orthogonal projection composed with the connection on Rn, right. So if the tangent vector is if x prime is perpendicular to the tangent space set to M, this is actually identical to the statement that along this curve the covariant derivative of x is identically 0. Okay, just I mean, if you take this connection to be the orthogonal projection of the Euclidean connection. So such vector fields are defined to be parallel vector fields. So here's a definition. So X is called parallel of course with respect to the connection nabla so parallel along this curve gamma if dt of x is identically 0. Okay. So in the next lecture we will talk more about these parallel translations and prove an important theorem that these parallel translations always exist. Okay. And then using that we can give a much more geometric definition of geometric characterization of the connection. Alright, so that's it for this lecture. Thanks for the attention and I will see you in the next lecture.